I want to just make a note about these polyatomics, and when we're balancing equations, this is a useful chart to have handy when we're doing some of these things, because a lot of times these elements will kind of move around together. So you can kind of avoid having to kind of recount all of these groupings as long as you're keeping track of the different kind of parts here. So if I have a ClO2 or a ClO3, that these elements might shift around from one element to and kind of pair with another. So let's say we have like lithium or potassium, right? They might change partners, but this grouping might just kind of move around. So you can just kind of keep those as a grouping. You don't necessarily have to break them down into their fundamental elements like chlorine and oxygen. You can certainly, it should work out either way, but sometimes it goes a little faster if you kind of group these. And sometimes I will try to do this, but sometimes you will notice that these elements are a lot of times not written with brackets or parentheses around them. So you'll have to kind of be able to see sometimes if it's a polyatomic ion, that it is a polyatomic ion that can fall apart. So it's just something that to be aware of to make sure. And then I will try to put these in parentheses, but just recognize that other textbooks or other sources won't always put those in parentheses for you. So we're going to start off with looking at some ionic chemical reactions. And a lot of times this is really, how do we make an ion? An ion is a charged element. And the way that we will make an ion is by the elimination of an electron. So sodium, we spoke about during the periodic table trends idea. Sodium will typically be able to lose an electron fairly easily. Chlorine, luckily, likes to accept electrons. So when that happens, we get a positively charged sodium because the electron left it, the negatively charged electron left, and then it bumped onto the chlorine or the chloride now. So this is the ionic form of both of these. And then when they come together, they will create a salt compound. Typically when we're looking at ionic compounds, these are really lattices. So if you take salt from a salt shaker and look at a little grain of salt, there are thousands and millions of elements of chloride and sodium ions in there. They're packed together in a crystal structure, and they are, there's not really one. Sodium doesn't belong to any one of these four chloride ions that are associated with it. They kind of all are sharing that positive negative charge, and they're distributed evenly. When we do this for accounting purposes, we just use, for the formula unit, we use the smallest whole number ratio. So for sodium chloride, it's a 1-to-1 ratio for every, right? And that means that we're canceling out the positive and negative charge to make it be zero. So the least number of elements that we can combine to make a neutral compound, that's what I'm talking about with the whole number ratio to neutralize it. So because this is just a plus one and a minus one, just 1-to-1 ratio cancels out that charge to give us a 0 ratio. Now when we get to other elements that have +2, +3, +4, +3, 7, whatever charges, then we can have different ratios of these that will have to be as the ratio for canceling out the charge. We'll look at that in a second. So one of the things we don't want to do is, for example, if you have sodium chloride, it's 2 sodium and 2 chloride atoms. That's not how you would write it, because we can simplify that. We can just have 1 sodium element, 1 chloride element, and that's enough to cancel out that charge and give us a 0 charge. So this is the formula unit, should be the most simple form of that ratio. Here's some rules for writing ionic formulas. The cation, the positively charged element, is given first in the formula. The subscripts must produce a neutral unit. So if I have a +2 and I have a +1 element, I need two +1 element or -1 elements. I need two of those minus elements to cancel out. So the end result, when those things come together, we have to have a neutral compound. Subscripts must be the smallest whole numbers possible. That's where we're simplifying it to the least number of elements given. And the charges on the ions shouldn't be included. So they're not part of that final, the charges aren't part of that final thing. You'll be able to get that information from that small unit formula, but they're not included there. Again, no subscript. It implies that there's just a 1 there. And let's look at some examples here. Magnesium oxide. Magnesium is from group 2A, so if you're looking at your periodic table, it's in the second group, so the second column. And it typically, those are going to form +2 ions. The Mg +2, so that's one of the elements we're going to look at. And then with oxygen, it's going to form, it's in the 6A column, so a couple groups away from the noble gases, it's going to form a -2 ion. So these two coming together, if we have a 1-to-1 ratio, that gives us an electrically neutral particle. And so the formula is going to be magnesium oxide MgO. So that is how we would put those together. It's the simplest form with the lowest whole number possible for both of those. One thing I want to talk to you about is this idea of the crisscross rule. So it takes into consideration the magnitude of the charge. So that means what the charge value is. Is it a +1, a +2, +3, etc.? So when doing this, again, this helps us, we want to make sure the subscripts are reduced to the lowest number, but the crisscross rule helps us understand how we can get these things to come together. Let's look at an example. So aluminum, a +3 element for aluminum, and then oxygen, -2. How do we put these together so that we can get a neutral element? So we think about the crisscross rule. Crisscross rule is you take the charges and you swap them. You put them from the charge spot in the upper right-hand side to the other element's lower subscript value. So now I'm going to write this out. So we have aluminum oxide. I've taken that +3 charge up here and I've moved it down below to refer to how many oxygen elements we need. And then the oxygen's a -2. I put that down by the aluminum. Okay, so does that make sense? What does this tell us? This says that we have 2 +3 aluminum, right? And that is going to give us, if we add those charges together, that gives us a +6. Oxygen, we have 3 of those at a -2. And that gives us a -6. So that overall charge is 0. This is just a quick, easy tool that we can use to generate our simple formulas for ionic compounds. All right, one more of these. What we're going to do is we're going to take this element, we're going to move these down, right? So we'd have, oops, sorry, this should be a capital M. And then we have an oxygen, right? If I did the crisscross rule, I would have 2 magnesium and 2 oxygen. Well, remember, we need to make sure that that's the simplest ratio. And so because this is divisible by 2, we can get the MgO. That's the most simplified version. But it gives us a starting point at least, especially when we're mixing the magnitudes of those charges. That's a crisscross rule is a helpful starting point. Okay, your turn. So I want you to look at which of the following is a correct formula for the formula unit composed of potassium and oxygen ions. Where do you begin with this? So determine what the predicted ionic charge should be for each of the atoms. Again, you want to look at where it is located on the periodic table and use that to look at trends What are the typical charges for potassium based off of where it is on the periodic table? What about oxygen? If you don't remember, you might have to go to a previous PowerPoint presentation, the last one where we talked about the charges and some of the trends and some of the expected patterns for how charges are set up on the periodic table. Use the crisscross rule to move those charges to the subscripts, and then that should give you the answer. So upload your answer in our discussion board. Another discussion board question, so upload your answer to the discussion board. Give me the which of the following correct formula for the formula unit composed of iron 3 and sulfide ions. Here's another learning check with polyatomic ions. Same thing happens. We're going to, and feel free to put parentheses around and make sure that charge, that's part of, that whole entire molecule is charged. So the combination of all of those creates a charged state. And so put these together, same idea with the, I've given you the charges already, and you'll just do the crisscross rule and then make sure that makes sense to you. Upload that answer onto our discussion board. In addition to ammonium and phosphate, I'd like you to look up that groups on that list that I gave you for the table for the polyatomics. I'd also like you to look up strontium and nitrate and tell me what that ionic compound formula would be as well. Strontium nitrate. I also briefly want to just introduce you to this concept of hydrates, sometimes with some salts that you might order from various chemical companies. You'll notice that they'll have this little dot and then water behind it. So these are called hydrates, and basically the crystals that form, they're hygroscopic, so they'll actually grab water from the air and they bring those into themselves. So sometimes you'll get these little packets in certain electronic things or in a bag, for example, and they have these little kind of beads. Those suck in water so that it doesn't ruin your electronics or ruin your beef jerky, for example. They'll have those things in them to suck the water out of the air to reduce the humidity. So they're helpful. There are a lot of these types of salts that will do this. And just so you're aware, typically different salts might take on different amounts of water. So calcium sulfate likes to take on 2 water molecules for every molecule of this. Sometimes they'll take up 4 or 5 or 6, but that will be defined in that salt. So it's not tightly held, but it does suck it up, and it changes. Again, when we start talking about, I want to measure out so much salt, when you're measuring this out, if you know how much water is associated with that, you then can put that in your calculations. So typically these can be removed by heating it. Sometimes people don't really care that much that there's water in it, and they'll just account for that when they're pulling out their calcium sulfate, for example. They'll just make sure they add enough so that they know that they get enough of the salt in the solution they're making. Here's an example of a hydrate calcium sulfate with 5 units of water associated with it. It's blue, and then when you heat it up, that water evaporates out and then it turns white. Just something to recognize that hydrates exist and how to kind of deal with them. And this is just the chemical reaction that's happening here. We have the hydrate with the bullet and they're written right next to each other, versus plus water, where the water kind of left the salt, but it's still, you still have to account for it to create a balanced equation. So now I want to talk about naming hydrates briefly and quickly. So these Greek prefixes, we've talked about mono, di, tri, tetrapenta. This is just, calcium sulfate with 2 dihydrate, cobalt chloride, hexa, tri. So basically, typically these Greek naming systems are used for how many of those water molecules are associated. And here's the complete list up to 10. So that concludes right now what I wanted to talk to you about naming some simple ionic compounds. And next we're going to start talking about how we can take some of these chemical reactions and we're going to start utilizing that information in the chemical reactions to start solving some problems. If we want to mix solutions, how much do we add? How much are we going to get out of that chemical reaction? So this is the next step in that process.
One thing I want to make sure that we complete and that we do is that we look at this idea called formula mass. So we know that now looking at these different molecular or ionic equations, these subscripts tell us how many of each of these elements are found within a molecule, for example. What we're going to do now is determine this idea called the formula mass. And in order to do that, the first step is to know how many of each of these are in there. And then the next is to know how much each of these weigh. And then we're going to add that together. So I'm going to show you a periodic table. Here is a periodic table I like to use online. It's from PubChem. And you can basically click on different elements and it'll bring some information up about that element. One of those things is that we're going to use right now is the atomic mass. So here you can see that's 14.007 units, atomic mass units, and this is the average amount. So we'll talk about this. This is basically going to be the amount of protons and the amount of neutrons. It's going to be their mass combined. So as you go from, for example, we'll start with boron, it's about 10.8. Then we go to carbon, it's 12.011. Nitrogen, 14.007. So these are going to be increasing as we go from the left of the periodic table to the right, and then as we keep going up in number, because we're adding protons, we're also adding neutrons, which add weight. So to do the formula mass, we need to, that first example, we had nitrogen, which was 14.007. We had an oxygen, which is 15.999 units. So let me bring this back up. And we know that there are going to be two nitrogens. That means that we're going to have 2 times the 14.007 units that were shown on that last slide. We're also going to, we're also going to add the 4, right, from the 4 oxygen times the 15.999 units. And if we multiply these values together and then add them, we should get 92.01 atomic mass units. So that's the formula mass for that whole entire thing. So this next question, we're basically just adding another 15.999 units. So the setup is the same, 0.07 units plus, now we have 5 times 15.999 units. And if we do that math, we would get 108.009 units. That is a way that we can differentiate between different elements because their formula mass is going to be different. And that reflects that different number of elements within that molecule. Let's look at carbon monoxide. Carbon monoxide and carbon dioxide, they both have carbon, which is going to be 12.011 atomic mass units. And we'll also have an oxygen, which is 15.999 atomic mass units. Here we have this carbon. We have 1 times 12.011 units plus 1 times 15.999 units. And if we do that, we combine those together, we'll get 28.01 atomic mass units. So that's the formula mass for carbon monoxide. For carbon dioxide, we have 1 carbon times the atomic mass plus 2 times 15.999 units for that 2 oxygen that we have here. And this is going to be 44.009 atomic mass units. So you can again see that difference between the two different elements based on their different chemical makeup, and their formula mass is also going to be different. We'll use these ideas later in the semester, but it's something I wanted to bring up because it connects to this idea of being able to do the accounting for the element.